Greetings everyone. We are now ready to begin Unit 7, which is about equilibrium and elasticity. The first of those two things, equilibrium, can be defined as a state in which an object is experiencing no net force and no net torque. You must meet both of these conditions in order for the object to be considered to be at equilibrium. That is to say that the sum of the forces has to add up to zero, as does the sum of the torques. Now, we want to be careful here because there is a difference between static equilibrium and dynamic equilibrium. Whenever we have the conditions met that the sum of the forces equals zero and the sum of the torques equals zero, that does not necessarily mean the object is sitting still. Recall when we were doing Newton's laws that we could have constant speed even when the sum of the forces was equal to zero. Likewise, we could have some sort of constant velocity and the sum of the torques could still be equal to zero. But that's what distinguishes static equilibrium from dynamic equilibrium. So in static equilibrium, the object remains at rest, whereas in dynamic equilibrium, the object moves with a constant velocity. For our purposes, we're going to consider only cases of static equilibrium, but it's good to know that there is such a thing as dynamic equilibrium. Okay, so the first condition that we need to meet is that the sum of the forces has to equal zero. That's some way of looking at a translational state of equilibrium, so that the center of mass is not accelerating. If you have an object being modeled as simply a point particle, this is easy enough to understand, but if you have an extended object, then you have to go further with this. A point object, you don't need to really consider torques for, but if there is an extended body to the object, it could be rotating in some way. And in that case, we need to look at what net torques are on the object. We want those to be equal to zero for the second condition to be met. And that is a statement of rotational equilibrium, that the sum of the torques is equal to zero. So whenever you're approaching a problem involving static equilibrium, it may seem relatively straightforward at first. Okay, we've got to add up the torques, make sure they equal zero, add up the forces, make sure they equal zero. But there's a couple things you should bear in mind. One is that when you are drawing a free body diagram, since it's usually dealing with an extended body, rather than modeling the thing as a point particle, it's helpful to model it as an extended body free body diagram so that you actually create some length and width to your diagram. Number two is that it's helpful if you can choose a reference point around which you are measuring your torques that actually makes your choice easier to calculate. What do I mean by that? Well, if you can choose a reference point where a force is acting so that it has no lever arm, i.e. R equals zero, then you know that that torque will not go into your sum. And you are free to make this choice just as you are free to make any kind of choice in terms of coordinate systems. Okay, and then finally, if you're dealing with an extended free body diagram, the place where you indicate the weight of the object is going to be at the object's center of mass. Oftentimes for a regularly shaped object, that's just right at the center of the object. For an irregularly shaped object, you would have to find where that center of mass is, and that's where you would draw your weight vector, of course, as usual, always pointing down. So as I mentioned before, we have this freedom to choose a reference point as our axis of rotation to analyze what the torques are doing, and we are going to try to choose this in an advantageous way so that we can make our calculations easier. So let's take a look at an example, a simple example to start with. We have a meter stick being subjected to two forces of equal magnitude. One is applied at the 2 centimeter mark. The other is applied at the 98 centimeter mark, as you see in this picture here. And what we want to know is which of these statements is true about this situation. We want to look at both the force and the torque involved. So when you see that the forces are balanced, you can deduce that the force is actually in equilibrium. If it's the same amount of force, then the force up is going to equal the force down. But is that the case for the torques? Well, think about what motion, rotation, might occur if you were to apply a force down here and a force up here. Both of these forces are attempting to rotate the meter stick in the same direction. This force alone would result in some sort of counterclockwise rotation, but so would this force. So they are not actually canceling each other out in terms of torques. They are sort of adding together instead. And so this means that the object may be in force equilibrium, but it is not in torque equilibrium. For another example, let's consider a ladder which is propped up against a wall. We're going to consider the wall itself to be frictionless, but there is some friction between the bottom of the ladder and the ground. And what we want to know is what this minimum angle needs to be so that the ladder does not slip. Okay, first we're going to start by drawing an extended free body diagram of the situation. And we want to know which of these is the case. Well, according to our discussion just a moment ago, we know that the weight force should be acting down at the center of mass of this object, which for a regularly shaped object like this ladder will just be at the center of the ladder. Of course, all the choices indicate a downward weight force at the center of the ladder. The next thing we're going to need in our free body diagram is going to be a normal force up from the ground, right? So the normal force acting on the ladder should be pointing up, not down, so that eliminates choice A here. Then we want to know what's happening with the friction. If the ladder is to slip, in which direction will it slip? It will slip this way, right? To the left. So that must mean that the static friction is counteracting that and pointing to the right, not to the left. So that only corresponds to choice D. Now, of course, I didn't say anything about the last force on this free body diagram, so let's make sure that it checks out as well. The wall is pushing onto the ladder this way. Yes, the ladder is pushing into the wall, but remember in our free body diagram, we only indicate forces that are acting on the object, not forces that the object exerts on some other object. So choice D shows all the relevant forces in the places that they should be. Okay, so here's how we would go about solving this problem. The first step would be to apply Newton's laws. And in applying Newton's laws, we want to consider both the x direction and the y direction. So anything pointing in the x direction or that has some component in the x direction has to go into my sum for the x direction, and then likewise for the y direction. In this case, I don't need to resolve anything into components. Everything is either pointing in the x or the y direction, so that makes my life a little bit simpler. I've got the friction force pointing in the positive x direction minus this normal force from the wall. If it's in equilibrium, this has to add up to 0. In the y direction, I've just got the normal force up and the weight force down, and that has to equal 0. So what I'm concluding then is that the normal force from the wall has to equal the friction force, and the normal force from the ground has to equal the weight force. And so based upon what my definition of friction is, mu times the normal force, I can make a substitution in here that the friction force is going to equal mu times the weight. Now the next step in trying to solve this problem will be to think about the torques involved. So I want to make a choice about my reference point for my rotational axis that simplifies my life. In other words, is there a place I can put my reference point, my axis of rotation or origin, so that some of these forces are acting right at that axis of rotation, meaning that they have a lever arm equal to 0, and thus it will simplify my sum. If I place the origin in choice A, I see that 2 of these forces are emanating from that axis of rotation, and so I don't need to add them into my sum. That eliminates 2 out of 4 forces. Any other choice is either going to eliminate none or 1 of the forces involved. And so choice A is going to be the most advantageous. Of course, you could make a different choice. There's nothing wrong with doing that. It just makes your life a little bit more complicated. Okay, so with that choice of axis of rotation, we want to sum up the torques that are acting. Well, I've got a torque due to the normal force. That's going to be equal to 0, though. Remember, these two were chosen on purpose. Same thing with the friction force. Now, why am I giving these two things positive signs in the sum? If you think about it, they would result in counterclockwise rotation, and so they get positive signs. This weight force, though, I'm giving a negative sign because if the weight force were the only force acting here, it would result in some sort of clockwise rotation, which by our sign conventions gives us a negative sign. And then finally, we'll add in the torque due to the normal force on the wall. Okay, the first two of these are 0. Sign didn't even really matter for those since we knew they were going to be 0. The torque due to the weight force or gravity is going to be the weight, mg, times the lever arm. Well, what is the lever arm? The lever arm, it's acting, if this is the entire length of the ladder, it's acting halfway. So we have L over 2, and then times sine of the angle in between the weight force and the lever arm. So what is that angle? Well, this is theta, right, over here. So here, this is actually 90 degrees minus theta, right? Because this is the direction of the lever arm, this is the direction of the force of gravity, so this is the angle in between. So we want actually the sine of 90 degrees minus theta. And then for the normal force on the wall, this is just the force times the lever arm times sine of theta. Well, this lever arm in this case is the entire length, right? Because this is my axis of rotation. It's the entire length, L, times sine of the angle between these two things. Well, this is these are parallel lines, and this is alternate interior angles. So this is my theta, the familiar theta that we have below. Okay, so if we then simplify this, this is going to tell me that mg L cosine of the theta is equal to 2pl sine theta. Because recall that 90 degrees minus theta is the same as cosine, so I can make that replacement there. Okay, and then when I cancel off the L's, that'll simplify things a little bit further. And what I want to do is isolate this angle here. So mg over 2p is going to equal sine theta over cosine theta, also known as tangent of theta. Now, based upon what I learned earlier from Newton's laws, this P was going to be equal to the frictional force, right? And I concluded that the frictional force was mu times the weight force. So I can make that replacement here, that 2 mu mg equals tangent of theta. But I already had mg here, so these things cancel. And what I'm left with is 1 over 2 times the frictional coefficient. And if I plug in what that frictional coefficient is here, I will compute an angle equal to 51 degrees. Okay, so notice that in this analysis we had to use both Newton's laws and set the sum of the forces equal to 0, and then we had to sum up the torques and set those equal to 0. And since we had more than one unknown, we needed more than one equation, but we were ultimately able to solve for the angle that we needed. Okay, the only trick that may be a little bit less familiar to you is this idea of choosing the reference point for the torques so that it simplifies your life, and then making sure that when you're adding the torques you obey the sign conventions. All right, so let's do another example. This one is a little bit harder to picture, but let's see if we can do it. I have two different pictures here to give you both a top view and a side view. What we're doing is we're looking at a diving board with a person standing on the end. And we know some facts about the diving board, how long it is, what its mass is, what the mass of the diver is, and so on. And it's being held down by bolts on the end, and then there's a support pushing up on the diving board right around here from underneath. Okay. So what we want to do is draw an extended free body diagram of this situation first if we want to find out the force with which these bolts are being held. And so our extended free body diagram will look something like this. We've got the force of the bolts being pulled down. We've got the normal force of the support pushing up here. We've got the normal force of the person who is standing and pressing down on the diving board. And then finally, we've got the weight force of the object. And since it is acting at the center of mass, and we can consider this to be a regularly shaped object, that weight force will be halfway down. Okay, so for the torque question, when I add up the torques, I'm going to choose this reference point because then only one of the two unknown forces will appear in my equation when I add up for the torques. Other choices could be made, but this is the one we're going to go with. Okay, so with that reference point in mind, what are the torques involved that are left other than that one that we were just counting as 0? We are going to, if we go back, we're going to have a torque due to this force, and this force, right? And I've got to make sure then that these add up to 0 and that I obey the sign conventions. The normal force was pointing in the upward direction, which would result in counterclockwise rotation if it were the only force acting, and so that gets a positive sign. The weight force and the normal force of the diver onto the diving board, they should have minus signs due to the fact that they would result in clockwise rotation. So all those things are true of choice A here. So what about adding up the forces? Well, in this case, I just want to make sure that I include all the forces at work on this diving board and that I reflect that in the signs, whether they are acting in the positive direction or the negative direction. This is actually just a one-dimensional problem. We don't need to worry about X and Y. Everything's either pointing up or down. And so the positive Y forces will get a positive sign, like the normal force here, but the forces that are acting down get a negative sign, like the force of the bolt, the force of the weight, and the force of the diver. So that corresponds to choice C here. Okay, so what will I get out of my equation for the torques? Adding these all up and setting them equal to 0. Doing so allows me to figure out what the normal force is of the support onto the diving board. This is going to be crucial because I will need that in my other equation in order to solve for what I'm looking for, which is the force of the bolts on the diving board downwards. So if I simplify this equation, solving for that force of the bolts, then I can plug in the normal force that I found earlier in the previous slide, along with the weight that I've been given based on the mass and the normal force of the diver on the board as well, and I will be able to come up with a value of 1,140 newtons. So go ahead and go back and review some of these problems if you would like for extra practice. We will continue the discussion of equilibrium in the next lecture.